There's a green color wire is what? Potentiometer wire. This is called as a potentiometer wire. This is a standard cell. So AB is called potentiometer wire. Usually AB, I'll pick up 1 meter or 100 centimeter. What are the requirements? Uniform cross section. The wire must have uniform cross section and uniform resistivity. Uniform cross section and usually that's what will be preferred. Is a standard potentiometer wire means it's called a standard. It will have some thickness. It will have some resistance. So then what is the resistance RAB? Let me write it as say like equal to 6 ohm. Then resistance per unit length I'll define RAB by L. So this should be equal to how much now? 6 by 100 or 0.06 ohm per centimeter. Like this we define resistance per unit length. Resistance per unit length. So now a cell whose EMF to be measured. A cell whose EMF to be measured, I'll connect it here. Whose EMF is unknown. So first I'll start with a known EMF. So there's a galvanometer. Now what is a galvanometer? What type of galvanometer? I should pick up a galvanometer which will have 0 between the scale. Because here I'm interested just to the pointer in what direction current flows. I'm not bothered about how much of current. I'm interested only in the measuring. The only to indicate the direction is what I'm picking. So therefore, what type of galvanometer I'm picking up, which will have 0 in between the scale. So 0 on left side, right side will indicate the direction of flow of current. Then after this, a were like a jockey. So this will be it's a rod like you can hold it. A sharp edge will be there at one end, and here I'll connect a wire. To that will be connected a wire. And there's a wire that one. There's a wire. There's a connecting wires. And there's a simplified circuit what we have, where I place that. Let that be C1. Okay, let's come for that. What is overall our circuit will be? How do I just put a straight wire here? And its point C1 is this jockey J is movable. Jockey J will be a movable one. This is a galvanometer. Now, what is the basic principle of working of this one is? Why we should not experiment with galvanometer? Because I know galvanometer, the current which will be flowing here, I can control that. Usually, what is the EMF of cells? Will not be 100, no, will be of order 2 volt, 5 volt, 6 volt. No arm, that one. Even I can pick up a galvanometer with how much maximum current, let it be say 1 ampere. So there won't be current more than 1 ampere that will be flowing that one. But construction of such current galvanometers of large current is not possible. Usually current will be of order few milliampere. So that I'll take care with this one. And the EMF of cell will be 2 volt, 4 volt, 6 volt. Will not be 100 volt. So current will be flowing will be of order few micro or milliampere. So such galvanometers I'll pick up. The EMF of cells will not be 100, 200, 300. It will be 5 to less than 10 volt or even 20 volt also, no problem. Okay, now there's a standard. So this is the standard cells. This I'm not going to disturb. Means whose EMF I know value of E naught, R naught, everything. This is the known cells whose EMFs are known. Cell whose EMF is known. Okay, let's do one thing. The circuit we have to understand. Now, what I see that the current through galvanometer is zero at one particular balancing line. Let lightly go for that. Current through galvanometer is in fact zero. Then if current through galvanometer zero means no current will flow here. How the current through galvanometer, if at all any current through galvanometer flowing, should be like this in this loop. And no current through galvanometer. I'm putting Ig equal to 0. No current flows here. So there's a point AC1. So here we'll take the points E1, B1, we'll write it. These are the points A1, B1. Okay, let's come for that one. No current flows through the galvanometer. So what all the current that is from this cell will flow here. And no current through this. And it will not branch here. The current will take a path like this. So what is the current? Current through this standard cell will pass through a potentiometer wire and it will take path like this here. Then you see that as the current flows, will there be any drop across the VAC1? Yes, it is. How much VAC1 should be equal to I into the balancing length, what I obtained, let it be lambda 1. I'll call this balancing length as lambda 1. Let me write here. So no current flows through this, and this is a wire, connecting wire it is. Okay, this is what here now. Now let's do things. So there's no current flow. So VA equal to VA1. Is it VA equal to VA1? Similarly, VB1 equal to VC1. Symbols problem. I'll do one thing. P1, P2. We'll take it. P1. VA equal to VP and VP1 equal to VC1. As there's no current flowing through this particular path, so therefore VC1 equal to VP1 and VAP equal to VA equal to VP. Okay, let's come for this one. What are PP1? PP1 are the terminals. They are the terminals of this particular given cell. So give red color. So what are PP1? PP1 are terminals of a cell. PP1 are I think I'll use small a, small b. I think you are familiar with that symbol. I'll change things. This will be VC1 equal to VB. We'll stick on to that one. So what are A and B? A and B are terminals of a cell. Okay, now you see that. Is there any current through the cell? It's very clear. There's no current through the cell, no? Then what is VAB? So you're going to write the equation VA minus EK minus IG into RK minus VB 0. What is IG? IG is 0. Therefore, what is VAB equal to EK? Now come for this. Since VAB, VAC1 will calculate. What is VAC1? I into current flowing to this. Let's apply ohms of current into resistance of this. What is the resistance of the length AC1? Lambda is the resistance per unit length. Lambda into L1 will be the resistance of the wire of length AC1. And as we know, VAB equal to VAC1. So therefore, what is VAB is equal to I into lambda L1. So there's one data what we obtained. And what is VAB? VAB equal to EK. So therefore, I'll slide up. So therefore, what is the conclusion now? Ek is equal to lambda into L1. So this is the data. So already I know, I know uh, I into lambda 1. Ek is equal to I into lambda L1. Keep this data now. Let it be as it is. I know L1, I measured it L1, and I know known EMF. What I do now, in place of this, I'll connect now unknown EMF. SL, whose EMF is unknown. I'll connect it. The same circuit, E naught, R naught. SL, whose EMF is unknown. I don't know its EMF, that I'm going to connect it here. RU, EU. There's a galvanometer and there's a mobile. There's a mobile. Let it be in contact at point C2. This is A, B. This is A2, B2. Then again, I'll adjust the position of the jockey J such that the current through galvanometer is 0. So again, the same current I will flow through this. This I depends on what? Any expression can be right for I. So what is I is equal to? E into resistance of the potentiometer wire AB by R, no? As no current through galvanometer. There's no current through the galvanometer. Ig equal to 0. Here also, Ig equal to 0. Now, again, looking at this, so this balancing length, let me call this is L2. Let's write all one by one. What is VAC2 is equal to? From the diagram, no current flow. The current will not branch. The current here will not branch. So what is VAC? 2 is equal to VAC2 should be equal to I into lambda into L2. Then let's come for one by one, all this one. So as the no current flows through the cell, so therefore VA should be equal to VA2, the potentials. VA is equal to VA2. Similarly, VB2 equal to VC2. All together, VAC2 should be equal to VA2 plus VA2 B2. What is, we'll write EMF this one. So this should be equal to VA2 minus EU minus IG into RU minus VB2 equal to 0. What is IG? IG is 0. So VA2 B2 should be equal to EU. Equating these two. So therefore what we can write it as EU should be equal to I lambda L2. So two equations I brought it. The value of the bridge is balanced at one specific value of length L2. What happen? The current through the galvanometer will show 0 deflection. The pointer will be at 0. The pointer will be at 0 for the galvanometer. Why no current flows? The reason for that, the potential drop VAC2 The potential drop VAC2 is equal to VA2B2. Then no current will flow, but there'll be a flow of current here. There'll be a flow of current. So therefore now I got one equation, you see this now. So I got the equation. So what is this? EU is unknown. So, like what do you mean by EU? Cell whose EMF is unknown. EMF is unknown. This is known. Known EMF. Can I measure L1, L2? Yes, I'll take a scale, I'll measure L1, L2. Let me divide this equation 192. U by EK equal to I lambda L2 by I lambda L1. No need to measure I, no need to measure lambda. So what is the value of U is equal to EK L2, L1. What are L2, L1? They are called as balancing length. L1, L2 are called as balancing lengths. This is like a cell whose EMF is unknown. Cell whose EMF is known. So like this, what happened? A cell whose EMF is, I don't know. Can I measure S using the potential? This is a standard cell. We are not bothered this, sir. I don't know E naught. I think it doesn't matter. No. Somehow what happened if you know the cell whose EMF is known, if you bring it now, you can measure EMF of other cells, sir. But how do I come to know EK? So you go for Daniel and Lagrange cell. What you study in electrochemistry, that's a standard, no? Based on the how much of solution I fill up, all that particular thing, I'm able to make a guess of the potential. And it's almost exact. Up to 3 decimal places, it is exact. And it's a standard one. So therefore, I know EK. So like this now, the EMF of any cell, I can measure it. Now, what is the basic idea? Idea one I implemented, no? So what I did, a cell whose EMF you want to measure, what you should see that current through that particular cell should be made zero. How to make that zero? By using this network. This potential drop VAC2, I'll make that equal to the terminal voltage. I can never make equal to EU. I just making that equal to terminal voltage of this cell. And because of that, no current flows here. Then the terminal voltage will become applied EMF. That's what we are, just it's a simple trick what we are using here. So if you want to measure EMF of a cell, so what you should do here, you should measure, you should make terminal voltage equal to applied EMF. When that will become, when current through that cell will become zero. How to make current through a cell zero? By using this a standard cell and potentiometer wire. What is this green color one? This is called as potentiometer wire. Okay, there's a basic idea, this one. Okay, now let's discuss some few more cases are there. So that, sir, how do I come to know current through galvanometer zero? I look at the galvanometer, the pointer when it is at zero, I'll note down the length. Getting this condition? So this is about the overall. So the numericals will be very easy for you. The only thing is somehow you should understand the theoretical part. The idea one, what I said, that idea one is something very important. Now, sir, if current through galvanometer not zero, what will happen? And that's what the students will get maximum doubt. Yes, even you get a numericals where current through galvanometer, this is called like a key. I'll explain all this later. And now then let me take two circuits. This is a potentiometer wire. So some cell, let's not bother, and E. So what I do is like there's a galvanometer, there's a potentiometer wire, AB. And now you see this. I'm I'm going to just change this one. If this jockey, that one, are you seeing the red color one? It's called like a jockey. That one, it's a rod. It's a conducting rod where you can hold it on that plastic coating will be given, where you can hold it and it's movable. This is what happens here. The point C is movable. Fine, all of you looking at this. Now what happens if I keep the jockey near to the point A? Tell me how the direction of current will flow. In what direction the current will flow? So in what direction the current will flow? I will write the terminals here. I'll give the name for terminals. AB. Let me- No. If the jockey is near to A, how the current will flow through the galvanometer? Across the cell, you tell it. B to A or A to B? Tell me which potential difference will be more. I'll keep it here. So let me call this is some P1. Huh? Let me call this is P1. And tell me which potential will be more. The same, another circuit, I'll bring it. There's a small thing where you must have the basic idea. Yeah, no, we have two things are there. No, you look at this one here. So now somewhere the balancing length is here. When the jockey is here, this is a balancing length. Somewhere the balancing length. So definitely open, I brought it here. So from the looking at this, I can say now VAB is greater than VAP1. How the current will flow? The current through the galvanometer will flow like this. This will be the flow of direction of current. IG. So the current here will flow here. So here some other current here to write it. I1. Here there'll be some resultant current I. Then how much of this will be IG like this? Because according to the conservation of charge, so how much of current here? I1. Are you getting this one? So now if the current through galvanometer non-zero, it will become like a two-loop problem. You calculate the resistance CP1, then P1B, then the entire circuit will appear like this. Then the entire circuit will appear like this. You need not to bother big, just already KVL. So this will be one resistor, this will be one resistor. What is this resistance will be? RAP1, this will be RP1B, the resistance of length of wire P1B. Then this will be cell. Can you solve the problem? Everything comes like this. Yes, it'll be easy, no? You can manage. Then write loop equations, solve it. You can get the current through all unknown things, what all you want, you can find out. So when the current through galvanometer non-zero, it will come like a two-loop problem. You need not to bother much. Here's a galvanometer. So can you predict the direction of current through galvanometer? As apply KVL, then calculate the current through galvanometer, then you can say in what direction current flows. I'm just giving a rough idea it is. Now when the jockey is here now. So this jockey is mobile, no? It's a mobile point. Now if it is here, current will flow one direction. Somewhere here, current will be zero. The current through galvanometer zero. If I shift it on the right side of balancing point, then what happens? The current will change direction. So therefore, the current through galvanometer means now your task questions are, how do I come to know balancing point? How do I come to know balancing point? Balancing point, I'll call it as P. So what is a P? P is a balancing point, let me call. P is a balancing point, not P1. So somewhere P is here. So now what I do is I'll, I'll, I'll take the jockey like this. So if it is here, what's happen? Current will flow in one direction through galvanometer. Then as gradually move, then at point P, what's happen? The current through galvanometer will be zero. If I shift towards right on the balancing point, the current should change the direction of motion. So how to identify exactly balancing point? What you should do? You should move the jockey from one end of the potentiometer, not exactly at a somewhere. from here you should move. If the pointer starts deflecting towards 0, somewhere the point in the galvanometer will be at 0 now, balancing length. Current through galvanometer will be 0. Then if I further move it, if the pointer deflects on right side of 0, then what does it mean? Yes, this is the balancing point. So how to identify current through galvanometer 0 means not directly you switch on circuit, you don't get. Really you have to put effort. In a lab, it may take 20 minutes for you sometimes. It may trouble you for 1 hour. It's not that easy. On paper, okay, we are all paper tigers, sir. Very easy. Any question will solve it. In the lab, no, the same experiment you need easily 2 hours, not 1, 2. 2 hours you need. I'll discuss all the situations what will happen. So now, first of all, is it circuit, is it in a working condition? What you have to check it? You have to move the jockey from the left end of it. And as you move, if the pointer deflects towards the 0, then somewhere it became 0. The deflection, the pointer is at 0 point off in the galvanometer. Then again, if you further move, what will happen? If the deflection on other side of 0, then what happens? The circuit is in working condition. Then you can carry on the problem. Got this? So here I'll go for balancing point. So what is the balancing point here? This will be P2. So what is the length? Balancing length. So this, I think you should not call balancing length here. So there'll be some length, there'll be flowing here. And what about the current in this case? The current here will flow. Some other current, not this one, some other current, IG dash you call it. You know enough of KVL. This is I2, call this is I dash. Some values, huh? It will be, so we have to calculate. Then again RAP2, this will be RAP2. How to calculate RAP1? The length. It's not a balancing length. I should not write this one. It will have some length. Call X1. So what is this length? Call X2. So when current through galvanometer not 0, then I think it's quite simple, no? So how to calculate resistance RAP2? Lambda into X2. What is RAP1? Lambda into X1. So now a situation arises where the current through galvanometer will never become 0. Tell me what problem arises. What problem arises? You move from A to B. The deflection, the pointer will be only on one side. What does it mean? The EMF of cell, what happen, will be greater than the VAB. Because without this jockey, what happen, there'll be some drop, no? There'll be some drop. So there's a problem what we encounter. Means as you move the jockey from A to B, if the deflection is only on one side, what does it mean? The EMF of cell, what happen, is greater than VAB. So therefore, what happen, what you should do? You should increase the E naught value. So in the beginning of experiment, what we should do? We should move the jockey from A to B. When you move from the jockey A to B, somewhere in between or somewhere, what happened? The current through galvanometer should be 0. Then only what happened? The circuit is in working condition. Sir, if you move from A to B, current will never become 0. It just deflects from higher value and it start decreasing and will never attain 0. The deflection will be on either side of 0. In that case, what you have to do? The EMF of cell, this E itself is greater than VAB. So you increase E naught. There's a basic idea of the working condition, that one. So when current through galvanometer not if it is not a 0, its problem is very simple. What you should do? Just take help of 2 loops. Then whatever they ask you, write loop equation and calculate. How to calculate the resistance? Because you'll be knowing the length X2. With that X2, what you can find out? The resistance is, this will be the circuit. So you do have problems where there are no loops are there. Means like a current through galvanometer will be in fact non-zero. Write it non-zero. It's of no use. Data of this kind, situation of this kind is no use. So still few problems are there. You have to work out them. Okay, this is about how to find out the EMF, how to check is it in working conditions or not. So this we have brought it. Okay, now how to find out the internal resistance of a cell. I'll introduce a page.